Welcome everyone. In this lab, we will continue with the Alpine Fault dataset based in South Island. In this lab, we will estimate MMI, that's the earthquake intensity at each bridge. So we look at the bridges data set and we visually check it. So the background map is the South Island plot. So we'll pass the command background underscore map equals south underscore island dot plot open bracket color equal light gray close bracket. Bridges dot plot open bracket x equal ax equal background underscore map close bracket, and that plots the bridges in the South Island. Then we visually check the MMI dataset. Visually by passing the command mmi.plot open bracket column equal mmi comma legend equal true. So that plots this map here in the South Island. So 10 is where the MMIs are higher, is equal to 10. So you can see the higher values of MMI are along the Alpine Fault. Then we display column names of MMI data frame. MMI.columns is so these are the column names: MMI, comma geometry, comma south underscore island. And we display the columns of the bridges data frame. So by passing the command bridges.columns, so it contains the columns FID, comma bridge underscore num, comma line underscore name, comma bridge underscore name, comma bridge underscore type, comma ID underscore maximo, comma shape underscore length, comma lead, comma lawn, comma TLA underscore name, comma shape underscore LE underscore 1, comma geometry. Then we look at the shape of MMI file. So MMI.shape is 673 observations and 3 columns. And then we check the shape of the bridges file. It contains 699 observations and there are 13 columns. Then we find nearest neighboring bridges. So MMI dot S index dot nearest open bracket bridges dot geometry close bracket and square bracket 1 close bracket. Now what happens is that we are finding nearest neighboring bridges geometric data points in MMI geometry. So remember, MMI geometry is multi-polygon. Let's have a look at MMI once again, dataset. So we'll insert the cell above. MMI. When we print that, the geometry is, each of these are multi-polygons. And the bridges are the points. Let's have a look at that. Let's have a look. So you see bridges geometry, it contains the points. So what we are doing in this command is we are finding nearest neighboring bridges geometric data points in MMI geometry. So geometry, MMI geometry is multi-polygon, many polygons, and we are finding the neighboring bridges in the MMI geometry by passing the command MMI dot S index dot nearest open bracket bridges dot geometry close bracket. Now there will be two arrays that could be formed, and if you look at I'll just show that. We'll copy this. We'll pass that. Okay, so we can see that there are two arrays that are produced over here, and the length of let's look at the length of each of these arrays. Length of the first array will say 0 and close the bracket. 699, and so the first array is for bridges, and we want MMI arrays because we want to find the corresponding MMI in MMI data frame. So let's look at array 1, the length of it. Array 1, and the other one was 0. Okay, so we can't tell. So the first array is for the bridges, and the second array is for the MMI, because the first bridge will contain a lot of not applicable, because the bridges are the point geometries, and the second array will contain all the values, all the geometries which are not which has a value. So we'll take this array 1, and that's the MMI MMI index values for which bridges geometry are in there. So when we do bridges head, we see that the NIA index. So we assigned it to NIA ID underscore IDX column, and it prints all the NIA IDX. So if we just remove the head from here, it will print the whole data frame. So looking at that, so we see that NIA ID underscore IDX is here. So yeah, so it's 699 rows. And then we visualize NIA underscore IDX. Let's have a look at that. Background underscore map equals south underscore island dot plot, open bracket, color equal light gray, and we close bracket, bridges dot plot, open bracket, IX equal background underscore map, comma, column equal NIA IDX, comma, legend equal true, close bracket, and we run this. Okay, so what happens is that when we look at this graph, we see the higher IDX, the index values are the yellow ones, and then it goes to the dark blue. So dark blue is the lowest, and then the yellow ones are the highest index values. Okay, now let's check. So if you look at this, so one of the NIA underscore IDX value is 330, and let's see where it comes from. So we look at MMI data frame. is this. Now you can see that the index is not in ascending order. So for example, 0 row index equals 0 is starting with row value 9. So the names are different. So let's look at the index, the row number 200. What is the row number 200? You can see that the name is 255, and that is with MMI 6, the multi-polygon, and it's the South Island. We are looking for the name 330. So, show it you again. This name 255 is the name of that row, which are labeled differently. It's not in order, it's ascending order. So let's look at I location 250. Let's look at what this index number looks like. The name of that is 306. We are looking for 330. So let's look at 265. And the name is 321. Let's look at what 70 gives. 270. 326. And what about row number 280? What's the name of that? 336. Now let's reduce this to 76. 270, 332, say 74. 330. So one of the IDX number is 330 over here, and that comes from those are where this point geometry is in this index location, in this multi-polygon, is nearest to this multi-polygon, and MMI value is 6. So, and if we do dot name, and this should print 330. Yes. Now we extract the names of each data rows. So we say column I equal empty array, column name equal empty array. For I in range, length of MMI, colon, call I, append, dot append, open bracket, I, that will be the row number, and call underscore name dot append, open bracket, MMI dot ilog, and square bracket I. So for each of those row numbers, what we are over here finding is the name by typing MMI dot ilog square bracket I dot name, and we append it to call name. And when we display in the data frame form, pd dot data frame open bracket curly braces I colon call I comma name colon call name, and we close the brackets, dot set underscore index I. So this call I, we let it be, let's show you. So that's the data frame here. So in the data frame we have the columns I and name, and now we want to put this name as the index. So let's do that. Set index this is the column name. Okay, so those that column I is set as index, and then we have names. So column in the MMI data frame, the row number 3 has name 12. So if the geometric point, any geometric point of the from the bridges data frame is nearest to that multi-polygon in the third row of MMI data frame, for which the name is 12, and that will be printed in this column here, in this data frame column, NIA underscore IDX. So yeah, now we join bridges data frame to the right of MMI data where NIA underscore IDX equal row index of MMI data frame. A row index, row name, not index, row name of MMI data frame. So for each of the row numbers, there is a name. So for example, so for row number 672, there is a row name which is 1005. So we'll pass the command bridges equal bridges.reset underscore index drop equal true. So we are resetting the index of the bridges data frame. So we will insert an empty cell above, and fetched will show the bridges data frame. So the bridges data frame is like this, and we are resetting the index, so it's in ascending order, and we want to, if we don't put drop equal 0, let's see what happens. Run it. See, there is a index column created, and for which it contains the old index of the bridges data frame. So we want to drop it. So drop equal true. So now you can see that reset index column is dropped. So now we join it to MMI data frame, and we want the MMI values from the earthquake intensity values, and we put on equal NIA underscore IDX. And we don't have NIA underscore IDX in the MMI data frame, but what will it do is it will match these NIA underscore IDX values to the names of each of those rows. So so that is the thing. So if for example we don't have a NIA underscore IDX column in MMI data frame, so this command automatically matches NIA underscore IDX from bridges new column to the row names, each row name in the MMI data frame, comma, how equal left. Now how equal left, which means that bridges data frame will be put on the left, and then these MMI values will be put on the right. And close the bracket, dot tail, open and close bracket, and when we print bridges, display bridges data frame, we see that here MMI value 6.0 for NIA underscore IDX 330 and so on. Okay, so these are the tail values. We don't want tail over here. We want all of those values. We have to run these again. We lost previous data because we let it equal to tail part, and we need to run the bridges. We need to run the bridges commands again. So for vendors, we're reading the file, then we plotting, then we are creating geometric points, and then we are creating a geometry column by changing bridges to bridges pandas data frame to geo data frame on it, and then we update the coordinate system to EPSG equal to 2193, and then we look at the background map, and we plot the bridges on top of the background map. So this is it, and then here MMI plot here, MMI columns, bridges columns, MMI shape, bridges shape, length of MMI as index nearest bridges geometry. So, and then we look at this array, this second array. We want to put it as a new column in the bridges data frame, and that new column name is NIA underscore IDX. So we run that, and then we see that NIA underscore IDX is printed, and then we plot that NIA underscore IDX on the background map. Look at this, and we look at MMI location 274, name of that, and we extract the names. Get that, and bridges dot reset index drop equal true. Okay, so that's it, and that was only to show, and this is what bridges data frame look like after you join it to MMI data frame. So you can see when NIA underscore IDX is 665, then MMI is 5. So let's check that in MMI data frame. Check if it is correct. So check. MMI. So what we're doing is that MMI data frame and this NIA underscore IDX number is 665. Let's look at the row number for it. Okay, so the row number doesn't give let temp equal to print temp. So yeah, so we want the name to be 665, so we are checking the row number for that. Set above. So temp and name equal 665, and we want to subset the rows, and index row number 357. So row number 357, the name is 665. So if we do if we want to look at the I location, square bracket, so 357 let's see, so the name is 665 and the MMI value is 5. So this data frame that we got after joining bridges to MMI on NIA underscore IDX looks correct. Drop columns not required. So we don't require NIA underscore IDX any longer. So we will do bridges dot drop bracket NIA underscore IDX, the column that we want to drop, and we want to drop from x is equal 1. So rows are x is equal 0 and columns are x is equal 1. And we want it in place equal true, and bridge dot head, if we print that, so should be bridges. Okay, so why it's giving us error is that when we first run, near IDX's column is already deleted and we can't have that deleted again. So we'll remove that and we'll insert a new cell and we'll print that. Okay, so this shows that the NIA IDX column is already deleted. Now that could be also done by running this definition. So you put everything inside this definition, and what we're doing over here, definition nearest underscore geoms, open bracket, left underscore GDF, comma query underscore GDF, comma columns to keep equal none, geom equal none, and then the column. Left GDF is the geodata frame with geometry column, example bridges. Query GDF is geodata frame with geometry column, example MMI. And columns to keep is list of columns to keep from query GDF. And geom is a geoseries to use instead of left GDF geometry. So may not preserve index of left GDF. Okay, if geom is none, then geom equal left GDF dot geometry. And if columns to keep is none, columns to keep equal query underscore GDF dot columns. Left GDF, the column near IDX equal query GDF dot sindex dot nearest open bracket geo close bracket, and then the second array, which is 1. Left GDF equal left GDF dot reset index bracket drop equal true close bracket dot join bracket query GDF square bracket columns to keep, comma on equal near IDX, comma how equal left, and left GDF dot drop bracket near IDX, comma x is equal 1, comma in place equal true, and close bracket retain left GDF. Now this definition does the same thing, and we'll use nearest function to find the nearest MMI to each bridge. retain the MMI attribute. So what we are over here doing is that calling this definition nearest geoms, and we are putting bridges MMI, and we are columns to keep, we are assigning it to MMI. So bridges dot head, that gives us values here. Columns overlap but no suffix specified. Index MMI. Okay. Don't worry about that, because because bridges we already put MMI column, and when we do the background map, visual plot of MMI from bridges data frame, so background map equals South Island dot plot, open bracket, color equal light gray, bridges dot plot, open bracket, AX equal background map, comma, column equal MMI, comma, legend equal true. So we plot MMI values over here. So we see that the bridge, this point over here is very dark red, which means the MMI value is 10. And this very dark purple, this very dark blue is MMI 5, and this sky blue one is close to 6, and then this greenish blue is close to 7, and so on. And some of those data is missing, which shows that the geometry, the bridges geometry is not in any of those multi-polygons. So that's why we didn't get the MMI values where there are missing data.